and welcome to my talk about real-time sparse distance fields for games. Before I will present you about the project, I want to take the time to credit the people who are actually behind the project. And this is first of all Anton Schreiner. He was the lead R&D programmer, and he is part of the AMD Core Technology Group, which is in turn part of the AMD Game Engineering team. Guillaume Boisset, he did some initial R&D work for this project. So he developed a prototype for distance fields that was then taken by Anton to do his own research. Diarra, Jay, and Fabio also play an important role because they took the research work and made a product out of it. And this is also where I come in. I'm Lou. I'm a developer technology engineer, and my day-to-day job is to work with game developers very closely to help them optimize their games for AMD hardware, but also to support them in integrating AMD technology. And one of these is the presented project here. And now to the talk itself. In the beginning, I will quickly recap what sparse distance fields are, just to make sure that everyone is on the same page. And then I'm very proudly to present to you the project, which is Pixelizer. It's a real-time sparse distance field generator for games. I will talk about the algorithm and also about the optimizations that we've done to get it into real time. I will also cover the integration, so that you kind of get a feeling of the workload that's associated with integrating Pixelizer into your game engine. And lastly, I will talk a bit about how you can use Pixelizer into your engine. And one example is to use Pixelizer to compute global illumination. This last section is very future looking because it's based on a research project at AMD that's not finished yet. But it will give you a quite good idea to what can be done with Pixelizer, and also should inspire you to do your own work. So that's why we have this last section in there. But let's start with the recap. So what are distance fields? Well, a distance field is a function that gives you the distance for every point in space to its closest surface. So you can write that as d equals SDF of p. And by definition, it means that the space around p with a distance smaller than d is empty. If the space is not empty, then our distance field would contain errors, because then the returned distance d wouldn't be the distance to the closest surface for the point. So we assume that this field has no errors, so we know, okay, the space is empty. What we don't get from the distance field is the direction where the surface is. But nevertheless, just the distance is already enough to traverse the scene. Traversing the scene is done to find the hit point of the ray with the scene. And this is typically done in an iterative way. So you have the ray origin, here denoted as ray cursor, and then you have the ray direction. And it's not just ray cursor because you advance it in every step, and you advance it along the ray direction for the distance that you get from the distance field. Because you know anything closer will be just empty space. And then you just do it as many times until the return distance exceeds a given threshold, and then you can just consider it to be a hit. So now you may have noticed that in the previous slide, but also in this slide, I abbreviated distance field with SDF. SDF is a very common abbreviation that you maybe have seen already. And it typically stands for signed distance field. So a signed distance field gives you positive distances if the point is outside the mesh, and negative distances if the point is inside the mesh. Respectively, if we have an unsigned distance field, the return distance is always the absolute distance. So we don't know if a point is inside or outside a mesh. Generally, to generate a sign distance field is more expensive because we also encode more information in this distance field. But it's also generally less robust, especially if you don't know with what type of content you're dealing with. So if you have no control about the content, you basically have to assume the worst. And one example would be if you get meshes with holes, because then suddenly it's not clear anymore if the point is inside the mesh or outside the mesh, and what distance should you return, and how you should deal with this. And to kind of get rid of this problem altogether, you can use unsigned distance field because they don't have it. It's just always the absolute distance. And that's why in the following, if I talk about distance fields, I always mean unsigned distance field, because that's what our solution will generate. Since we don't have control about the content, we have to be able to also deal with meshes that may contain holes. So that's why the generated distance field is an unsigned distance field. So now you've maybe noticed in the title it's not just an unsigned distance field, it's actually a sparse distance field. So what is a sparse distance field? Well, distance fields are per se a dense scene representation. So for every point in space, we store the distance information. This is a lot of data, especially if you consider that most of the space is actually empty. So neighboring points in empty space, they don't have so much information compared to neighboring points close to surfaces. So the question kind of comes up and is, can we somehow group empty space to save memory? Because memory is very precious, right? We don't want to waste it on areas that contain very little information. And this is exactly what sparse distance fields try to solve. So they encode empty space differently and then have the distance information for space that's actually interesting for us. How empty space is encoded depends on the sparse distance field. But before we talk about how it's done in our solution, let's talk about how distance fields themselves are represented. Typically, it's done either analytically or via 3D texture. If it's an analytic representation, it can become very complex very quickly depending on the scene. And then when you evaluate the distance field, so you do the traversing and you want to get the distance for the point, it might involve a lot of computations. While with a 3D texture, the generation of the 3D texture can be quite expensive, but as soon as we have the 3D texture and you do the traversal, then it's just the texture lookup. And then it also doesn't matter what kind of meshes you encoded in the 3D texture. This only plays a role when generating the 3D texture. So how do you do this generation? So current solutions are often actually pre-baked, so it's offline, and thus they only work on static geometry. And here is where our solution comes in, because it's real time. This also means that it can take dynamic geometry into account. And before I go on, just a quick note to get rid of any confusion. If I refer to distance in the following, I always mean Euclidean distance. But now let's talk about Pixelizer. Pixelizer is AMD's solution to generate sparse distance fields in real time for any given triangle-based geometry input. So you have the geometry input in a triangle representation. So typically you have a vertex buffer, index buffer. You also need to transform information so that we know where the geometry is in your world. And then additionally to that, you also need to provide the axis-aligned bounding box, in short ABB. This information will be taken by Pixelizer, and then Pixelizer will do its magic and generate the sparse distance field that you then can in turn use to generate the ray point with the scene. So in the slide, you notice I say bricks and sparse distance fields. And what bricks mean, I will explain very shortly. First, stay a bit more high level. So Brixelyzer generates a sparse distance field. As I mentioned before, this means that there will be no distance field information for empty space, but we will have distance field information for areas close to surfaces. We can also say the Brixelyzer generates local distance fields that are close to surfaces. For empty space, Brixelyzer will use an ABB tree. So first, you traverse the ABB tree, and then once you reach the leaf nodes, you swap to traverse the distance fields. The distance fields themselves, as I mentioned before, they are a collection of local distance fields. And a single local distance field is called a brick. Bricks are generally close to surfaces. So if we lay out a 3D grid over our scene, for every grid cell, we determine if this grid cell intersects with a surface or not. If it does intersect with a surface, we let it point to a brick. If it does not intersect with any surface, it remains empty, so it will not point to anything. So in this example, the colored areas, these are grid cells that point to a brick. So we have distance field information for this area. The white grid cells, they will not point to any brick, so we will not have any distance field information for these areas. The grid cells, they will point to an atlas, and the atlas itself will store the bricks. The grid cells can also be called voxels. And yeah, the atlas stores the actual bricks, so the grid cells, or also voxels, as I mentioned, they will just point into the atlas, and then you read from the atlas the distance field. The atlas is of type REDU norm. The brick itself is 8 by 8 by 8, so it encodes a region of 7 by 7 by 7. The brick will not only store the distance field of the region it represents, but it will also store the ABB of all the surfaces that it intersects with. Why? Well, first some debug information to show you what we actually have represented in bricks. So first the voxels with the bricks themselves. So voxels means the grid cells. You see here you only see here the voxels that actually intersects with surfaces. If you would also display empty voxels, you wouldn't be able to see much because it would be just too cluttery. So you see on the left, I'm talking about the picture on the left. So voxels with bricks, and the bricks themselves in the form of the distance field they encode. So it's an approximation of the scene. And then on the right, you see that the bricks also contain the ABBs. So instead of visualizing the grid cell, visualize the ABBs in the right picture. And these ABBs are for the surfaces the bricks intersect with. And we have them because they are used to build bottom up the tree-level ABB tree. This tree is there to encode the empty space. So we take the ABB from the bricks, we build bottom up the tree. And then when we traverse the scene, we start at the ABB tree. So the ray just checks all the ABBs, if it intersects with it. If yes, we go down to the child nodes. And then at some point we will reach the leaf nodes, which means we are actually reaching the bricks. And then we will swap to traversing the distance fields. A Brixelyzer will always generate a tree-level ABB tree. This proved to be enough in our current experimentations, but generally the algorithm doesn't prevent to extend the tree. But this is just something that Brixelyzer does for now, but maybe it will be changed in the future. Maybe it needs to be changed only for a certain case. this still remains to be determined. But there are no limitations in the algorithm itself. Yeah, so once we traverse down the tree, we end up in a break. If you don't end up in a break, then the ray didn't intersect with any geometry in the scene, and it will be just a miss. But assume we are hitting a break, then we need to evaluate its distance field, and the distance field itself will be based on the triangles and not on the ABB, otherwise it would be very, very approximate. So that's one of the triangles. And just to remind you, a brick is of resolution 8 by 8 by 8, thus it has 512 pixels. And the pixel is a single unit within the distance field, and each pixel stores the distance to its closest surface. The region the break actually encodes, so the region in our scene, depends on the cascade and its resolution. Cascade, well, Pixelizer uses cascades, and they're typically centered around the camera, and this is to account for nearby objects and far away objects. So objects that are really close to a camera typically need a higher resolution than objects that are further away. And this is also one optimization, because this way we save on resolution for objects that don't need it because they're just so far away. Each cascade has its own tree-level ABB tree, but all cascades will point to the same 3D break atlas. So the atlas is shared among all the cascades. So this is Pixelizer, another debug view. This is just to give you a better idea of how Pixelizer approximates the scene. And if you look closely in this debug view, you can already see the different cascade levels. So if you look at the floor and go kind of down the path, there's like this kind of little gate. If you go to the back, so you kind of see on the floor at some point the breaks, they get a bit larger. And then especially if you look at the little hill, they even get more larger. So it gets more obvious. And so the breaks, they're just colored differently. So that's how you can see what one break is. And but here you see, for areas closer, you have smaller breaks. For areas further away, you have bigger breaks. And all of them are 8 by 8 by 8. So all of them have only 512 pixels, regardless in which cascade they are, so regardless about the area they encode. So how does Pixelizer generate this distance field that I just talked about? So this is done for each cascade separately. So if you have Pixelizer, we call an update function, and this update will only act on one cascade. So if you have, let's say, 2 cascades in your scene and you want to update them both, then you have to update, but then you have to call update twice, once for each cascade. And the whole process to generate the distance fields, the ABB tree, is done via an voxelization pipeline. And the voxelization pipeline can be roughly separated into 2, with the ABB tree construction into 3 parts. First is the voxelized part. So in this part, we identify the grid cells that intersects with surfaces, and then we let it allocate the break. And in the following, I will call each grid cell a voxel, just to be a bit more consistent with the terminology. Once we determine which voxels intersects with surfaces, we create a break, and then we go to the second phase, where we go into each break and fill it out with the distance field information. We also generate the ABB, which is then used to build bottom up the ABB tree. So in the very beginning, we have our input, which is the list of the geometries and the ABBs from our scene that we want to process in the distance field. And first we do some general culling to get rid of all the geometries whose ABBs do not even intersect the cascade grid. Yeah, because we don't want to waste any computation time on them. And then we start with the voxelization part itself. And for this, we scan all the geometries and we count the triangles they have. And then for each triangle, we spawn one thread. And each thread scales the triangle's ABB. So one thread is responsible for one triangle. And it takes the triangle's ABB, it scales it to be a voxel size unit. And it does that because then we can simply take the volume of the ABB, and this gives us the maximum number of possible triangle voxel combinations. So the maximum number of voxels that this triangle can intersect. So in this small example on the slide, we have the triangle, its ABB, we scale it to be in voxel size unit, and the volume of it is 2, so the maximum number of voxels this triangle can intersect is 2. And this gives us, for each triangle, a list of possible triangle voxel intersections, and each of this triangle voxel pair is called a reference. So you have, for each triangle, a list of references. The next step is to process these references, because we need to verify if it's actually a valid reference. So if our triangle really intersects this voxel and not just its ABB. And this way we end up with a list of voxels and the triangles it really intersects. So this is the end result of this step, that we have for each voxel a list of triangles. And this also will identify the empty voxels. So for empty voxels, we are done at this stage. For non-empty voxels, we allocate a new brick. Each brick is 8 by 8 by 8. Each pixel is 8 bits, and it encodes the distance between 0 and 1, and it's normalized to the linear brick size. This is important when you read out the information. But yeah, so each brick needs 512 bytes. So we allocate the new brick. And then we want to fill it with the distance field information. And each thread group processes one brick, and each thread processes one triangle. And it just checks for triangle brick cell intersections. So brick cell is a single unit within a brick. So it just checks for the intersections and then it stores the minimum distance. This gives us a partial distance field, I would say, because some pixels will have the minimum distance, but other pixels, they won't have any distance because they are not intersecting any triangle. At this stage, we also compute the ABB for the brick, which is needed for the ABB tree. But yeah, so after the stage, some pixels are still empty, so we do another step, and this is to use iconal to fill in the gaps. So it's a type of jump flooding algorithm. I will not go into detail into what this exactly is. If you want to know more, please check it out. There's plenty of information in the web out there, but just in short, it's a way to kind of distribute this information we already have to the remaining pixels, so that in the end, that for each pixel we have the distance information to its closest surface. Please also note that when we do this, filling out the bricks with distance field information, that neighboring bricks will actually have the same border pixel values. So here in this example, we have two bricks, a blue brick and an orange brick. And their neighboring pixels will actually encode the same spot. And for both bricks, this pixel will store D0. Also for the orange brick, even though D0 encodes a distance to a surface, that does not intersect the orange prick itself. And this is achieved by expanding the triangle a little bit when we do the triangle and prick ABB intersection test. And this is to ensure exactly this property, that the border pixel values share the same value. In this way, we achieve C0 continuity. Quick overview again. So we first voxelize the scene. So we get a list for each voxel with all the triangles it intersects. And we create a prick for every non-empty voxel. And then for the pricks, we fill it out with the distance field information. We also create the ABB for the prick, which is then used to build bottom up the ABB tree. So optimizations. I present to you the basic algorithm, but there have to be done some optimizations here and there to get it up to speed so that we can actually do it in real time. And the first very important optimization is to make a differentiation between static geometry and dynamic geometry. Because static geometry does need to be revoxelized each frame, right? Because, it doesn't change. And it would be a waste of computation if we would revoxelize it each frame. So optimization is to not do this. So there's a way for Pixelizer to cache the results and just keep it persistent. To achieve this, Pixelizer only creates new bricks for voxels that do not point to any prick yet. So if the voxel already points to a prick, this voxel will be completely ignored throughout the whole voxelization and ambient distance field pipeline. So how does this work in practice? So in the beginning, we have a completely empty grid, and then we have some geometry that we want to process. Since the grid is completely empty, all voxels will be considered, so we just go on as described previously. We just check which voxels the geometry intersect with, and then we create bricks for these voxels. Now, if at some point new geometry comes in, so we had the dog, and now we also have a turtle. When we do the update, we still check all the geometry. So we check the dog, we also check the turtle. But when doing this check, Pixelizer will notice, okay, the dog only intersects with voxels that already point to a prick. So it will not do anything with them. It will just leave them as they are. While the turtle will intersect with empty voxels, so for them it will generate new bricks and generate the distance field. So this is fine until you get a new geometry that intersects with voxels that already point to a prick. So we have the cat, and we do the voxelization process again. So we check which voxels do the dog intersect, which voxels do the cat intersect, which voxels do the turtle intersect. And we'll find out, okay, the cat intersects with 6 voxels, 4 of them are empty, fine. But 2 of them are actually not empty. I mark them here as with red voxels. And since they're not empty, they will be skipped. But this is actually wrong, right? Because this way our distance field would represent a cat without head. And that's clearly not what we want. So how do we solve this? We need to add a preprocessing step. In this preprocessing step, we determine which voxels might possibly intersect the new geometry. So in this case, the cat. And these voxels will be marked. Marked means we just free them, because once they are freed, they will be reconsidered during the voxelization step. So we kind of check which voxels will intersect the cat. We mark them as free, and then when we do the voxelization, we do the usual job. So the formerly red marked voxels are here now marked green because they get new pricks created. And now when we generate the distance field for these new pricks, we will take into account the cat information, but also still the dog information. So the distance field will be correctly represent a cat with head and also a dog with legs. Everything's fine. Now the question is, how do we determine the voxels this geometry possibly intersects with? we do the same thing that we already did with the triangles. So we take the ABB of the geometry and we scale it to voxel size unit. And for the triangles, this gave us the maximum number of possible intersections this triangle had with the voxels. Now with the geometry, this gives us the maximum number of possible voxel and geometry intersections. For the triangle part, we did verify if this reference was valid. For this case, so for these geometry references, we just don't verify, we just clear all of them, because verifying would be more expensive than the time we would win by not clearing voxels that actually don't intersect the geometry. So in this way we just clear them, and then they will be reconsidered for voxelization during the update. So this was static geometry. How does Pixlr deal with dynamic geometry? So dynamic geometry needs to be reprocessed every frame. Well, in every update, every frame depends if you call update every frame. But yeah, so on every update, we need to reprocess the dynamic geometry because they have changed. Which basically means that we just rebuild everything from scratch for dynamic geometry. In order to support this, Pixelize actually has two separate cascades. One for static geometry, one for dynamic geometry. And the one for dynamic geometry is completely cleared at the beginning of each update, and then it will just rebuild everything from scratch on update. At some point, we have to merge the static cascade with the dynamic cascade so that we actually have a distance field that has both information in it. And the merge happens before the iconal jump flooding stage. And it's per pixel. So when we emit the distance field to the step where we kind of build in, like filling out the brick by checking all the triangle pixel information, we do this separately for both static and dynamic cascades. Then we do the merge, and then we do the iconal based on the merge cascade to propagate the values to the remaining pixels that don't have any distance information yet. The ABB tree is also based on the merged cascade. And this is just a little debug video to demonstrate to you that Pixelizer does support dynamic geometry. So here you can see how the grid, like the voxel that intersects with geometry, update, and the new distance field just gets generated in one time. Yeah, that was all about static and dynamic geometry. And now about the cascade updates and how to call it. As I already said, an update is per one cascade. And actually you can even only do a partial cascade update. So for example, if your camera moves, a part of the cascade might still be valid, but another part of the cascade needs to be updated because it just represents like a region that we haven't processed before. And this is done by just moving virtually the center of the cascade. So you don't need to copy any data around. And the data is addressed totally with respect to the center. So this is one way to speed up the processing, that we just update what's really needed. Another way to improve the performance is time slicing. So as we need to call an update for each cascade separately anyway, we can also decide how we call these updates. And of course, it's always the trade-off between update performance and the cost of some latency. I mean, you can update all cascades every frame. You can also just update one cascade per frame or just half a cascade per frame. What's the best strategy really depends on your scene and also on your requirements. But yeah, it is possible to choose different strategies. Pixelizer will propose one strategy. This is to update the first cascade every even frame and the others every odd. This is done because it's considered that the first cascade is the most important one because it represents the areas closest to the camera. And then as further away the cascade gets, the less often it gets updated. But this is just a proposal of Pixelizer that can be used but doesn't need to be used. Then doing the voxelization pipeline itself, there are two steps which actually have a bit of unbalanced workload, and the optimization is to rebalance it. And one is when we process the triangle references. So we spawn one thread per triangle. So first we counted all the triangles of the clone tree, right? And then we spawn one thread per triangle. And each thread determined the number of references, so the maximum number this triangle possibly intersects with voxels. And then we had to verify if the reference was valid or not. So we could let each thread go on to stick with its triangle and to just process all the references of this triangle and to verify if they're valid or not. But yes, this can lead to quite unbalanced workload because some triangles will have a lot of voxels they might possibly intersect with, and other triangles might have just a very few. So instead of just letting each thread stick to their triangles, we store all the references to group shared memory. And then once all the references are stored in group shared memory, we let the thread abandon the triangle and just pick a reference based on the reference ID from the group shared memory. And they just don't care to which triangle it belongs to. And in this way, the references, all the references from the whole thread group, gets distributed to all the available threads. Another workload balancing is done when we compute the distance field for the bricks. So one thread group works on a single brick. But now some bricks intersect with many triangles, others with very few. And to balance the workload a bit better, the work is actually split up for bricks with many triangles. And it's split up in so-called sub-voxels. And each sub-voxel processes 32 triangles. And one thread group works on a single sub-voxel. So you basically, for every 32 triangles that a brick intersects with, we spawn a new thread group. Talking about triangles, Pixelizer handles small triangles differently than not small triangles. And this is done to save memory and also speed up the processing. And we can safely do this because at a certain point, a triangle is so small that being more accurate, you wouldn't be able to see it because of the resolution of the brick. This also means that to say if a triangle is small or not depends on the brick. So Pixelizer will consider a triangle to be small if it's smaller than 1/10 of a brick, which means it's smaller than a single pixel. So what this in real terms is, the actual threshold depends on the brick, and it depends in which cascade this brick is, what the resolution of this cascade is. Yeah, in a small triangle, for a small triangle, we only store the center of the triangle, and then this center is used to do a point approximation to determine the distance from the triangle to the voxel, to the pixel, wherever we need to do this triangle intersection test. This way we also only need 12 bytes for a small triangle, whereas otherwise we need 24 bytes because usually we store one vertex and two edges. Then we have some upper limits during the process. So there is a limit on how many references are processed per frame. This limit can be changed, so it kind of depends also on the scene and also on the performance requirements. And it's there to prevent the processing time to suddenly explode. So there's like a limit. You can say, okay, if we have more references, we just will do it in a later frame. And then there's also a maximum number of bricks we can allocate per bake. If we exceed this limit, then an invalid brick ID is returned. So currently the 3D brick atlas has a fixed size. So we can't allocate more bricks than this atlas has size for, and the current size has space for 256,000 bricks. If we need to allocate more bricks, then actually the cascade has to be tuned. So you have to change the size of the cascade, maybe also the resolution, and what's appropriate really depends on the scene. So, performance. I mean, we did all these optimizations to get Pixelizer into the real-time sphere so that it can do all this processing at runtime. Performance is influenced by a lot of different factors, so it's very difficult to give hard numbers because you can tune it on so many different levels and it's so scene dependent. Basically, during the process, the time depends on how many voxels are touched. It also depends on how many triangles are processed, and then ultimately how many bricks need to be baked. All of these three entities, they also have a somewhat overlapping influence, but not entirely. So they do influence different parts, but then also sometimes the same parts, if that makes any sense. But yeah, so all three entities of them are kind of important to keep an eye on to make sure that the performance is where we want it to be. And then there's also a small overhead involved in general state tracking and cleanup, and that's needed for every cascade update, even if you don't update anything in the end, because there's just no new geometry. So it's just basically update on a static scene and nothing has changed. So there's still this kind of general state tracking cleanup, but it's really small overhead. And yeah, so it's really important to tune the parameters accordingly because they can affect the performance substantially. But yeah, in general, on our preliminary results, so they might change in the future. They are based on a pre-release version of Pixelizer. We're still doing optimizations as I speak. These preliminary results, they show that as long as you stay in the thousands, so several hundreds of thousands for any of these entities, you generally also stay under a millisecond that it takes to process this entity. This can involve several steps during the pipeline, but again, it also depends on what kind of property this entity is. So how many triangles, how large are the triangles, and so on. If you go for any of these entities into the millions, then also processing time can take a few milliseconds. And of course, if you go crazy on the number of entities, then the processing time can also go crazy. But yeah, it is definitely possible to do the processing step to keep it under a millisecond if you're careful. And yeah, the test system had an RX 7900 XTX, and it used the driver from February, so the 23.2.1 driver. And as I said, it's based on the pre-release version of Pixelizer, and we are still doing optimizations, so the numbers are likely to change. Current limitations with the presented project with Pixelizer. The first one is, of course, memory management. I mean, Pixelizer does use a sparse distance field, and the purpose of sparse distance field is also to save memory, but of course the fundamental problem remains. There's always a trade-off between precision and memory consumption. Then precision is the next limitation, because Pixelizer will generate an approximation of the triangle-based scene. So if accuracy is all you want, then just use the triangle-based scene directly. But Pixelizer generates this approximation that's then very efficient to evaluate. That's the purpose of Pixelizer. But yeah, this precision differences. So the fact that Pixelizer just runs an approximation, it can get visible for near field objects. Also, Pixelizer does not generate a global distance field. It's only generating a collection of local distance fields. We do have C0 continuity, so neighbor values match. Gradients, they are not continuous by default on the brick boundary. Also, distance fields only provide a point in space as a hit point. Right? Maybe you also get the gradient, but as I said, it's not C1 continuous, it's just C0 continuous. But yeah, anything else needs to be added manually on top of Pixelizer. So Pixelizer only gives you the hit point with the scene of this ray. But that's basically all about Pixelizer itself. Now the question is, how do we integrate Pixelizer into a game engine, and what's the estimated workload? So Pixelizer will be part of the new AMD FidelityFX SDK. This means it will be open source, cross-platform, and of course highly optimized. It runs on any DX12 compatible GPU. It will be provided via library. We will also provide the full C++ and HLSL source with an API documentation to enable custom integrations. There will be also a sample provided with in DirectX12 to demonstrate how to integrate Pixelizer. Since it will be part of the new AMD FidelityFX SDK, it will also use the FidelityFX interface that every other FidelityFX effect is also using. If you want to know more about this interface, about the general structure of all the FidelityFX effects of the SDK itself, I highly recommend you to check out the FidelityFX SDK presentation, which is also a GDC presentation of this year. And it will be also hosted as a video on GPU Open for reference. But how to integrate Pixelizer itself? So the basic is that you add the header file. This is kind of the same for every effect. So this ffx underscore for Pixelizer is bx. And there's one peculiarity for Pixelizer, because here are two headers you can choose from. One is the one you're used to, so fx underscore bx, and then there's also a simple version. And this is because Pixelizer offers two API versions. One is a low-level API, if you really want to have control over every little single thing. Or if you want a simplified API, this is much simpler to use and gets the job done for most use cases. So I recommend to start with the simple one, and then once that's integrated, then you can go down to the lower level API if needed. You also have the option to either link to a static library or to just take the source code and do a native integration. Then Pixelizer itself, well, there are a number of function entry points, some related to the context management, then to cascade management, which basically means to generate the distance field. So this is also a topic of how to import the geometry in the ABBs, how to call the update function. And then lastly, some tracing and debugging functionality. So to debug, you kind of need to trace the distance field. And Pixelizer will help you with this because it's needed to verify that the integration was successful or not. The context, so usually you have one context per scene, and the context will have all the cascade information. So you have a center that is shared for all cascades. Then you have the number of cascade levels. And then for each level, you can specify if you want to have a static cascade and or dynamic cascade. So typically, I would expect that you have both for each cascade. So both a static and a dynamic cascade. But maybe for performance reasons, you don't want a dynamic cascade for the higher ones. So for regions that are far away, because you don't want to display dynamic objects for very far away objects. So this could be one use case where you only want to specify that This cascade level only has a static cascade, but yeah, typically you have both. If you want to know any more information, please check out the official documentation for details. Once we have the context and the cascades specified, we want to populate the cascades and update them and process the geometry. So we somehow have the geometry to get into Pixelizer. And this is done via instances. So geometry, again, is represented via vertex buffers, index buffers that transform information so that Pixelizer knows where this geometry is in world space and also its ABB. And with this information, you create an instance. And an instance is Pixelizer's internal representation of your input. There are two different types of instances. One is a static instance for static geometry, and one is the dynamic instance for dynamic geometry. In case of a static instance, Pixelizer will return an instance ID because this is used to uniquely identify the geometry in its ABB and also to do general state tracking of this instance internally in Pixelizer. The IDs are persistent, and it's also recommended that the application takes track of it to verify whether geometry has been already processed by Pixelizer or not. Static instances also needs to be deleted manually, so the application has to say, hey, this instance has to be removed. Reasons to this is because the instance is suddenly too far away, you don't see it anymore. It's destroyed also for semi-static geometries. So one example would be a door. A door usually is just a static object, but sometimes it suddenly turns into a dynamic object when the door opens. So these type of objects you want to have in the static cascade. And then on update, you simply delete the instance and create a new instance and put it into the static cascade again. But yeah, this is another reason to call the delete instance function. And this just removes the instance from Pixelizer's internal instance list. And yeah. And really to do this, appropriately is in the responsibility of the application. So the application has to stream in and out the geometry such that it makes sense. There is a maximum number of supported instances that Pixelizer can handle, and that is currently at 64,000. Dynamic instances do not need to be deleted because they are deleted automatically every frame. Why? Well, you don't need to keep track of dynamic instances. You don't need to cache their state because they get rebuilt on every update from scratch anyway. So how to do the update? This is done roughly in 3 steps. So first, you need to fill out the update description. And to do this, you can call SimpleBake update because this function will populate the update description for you. So it will queue the instances to the correct cascade. And this is done via so-called job list. So job list just has the cascade, but jobs needs to be done to get properly updated. So we have a job list for the static cascade and we have a job list for the dynamic cascade. For the dynamic cascade, it's pretty simple because it just contains all the dynamic geometry. For the static cascade, it's a bit more complex because of the reason that I talked about earlier. Some voxels have to be preprocessed and marked as free because they possibly intersect with new geometry. To do this, we have so-called invalidation jobs, and they just clear the voxels. And we have invalidation jobs for new instances and for destroyed instances. You don't need to worry at all about these invalidation jobs because Pixelizer will generate them automatically for you. So you just create a new instance as needed and delete it as needed, and all this invalidation will be handled by Pixelizer. But yeah, Pixelizer needs to handle it to prevent that we don't have headless cats running around suddenly. If we have more invalidation jobs than twice static instances, then Pixelizer will take a shortcut and will just clear the whole cascade. and clearing the whole cascade is done anyway for the dynamic cascade. So that's quite simple. This simple bake update does not only create the job lists, but it will also update the cascade update description for you, where it will populate it. And it will populate it with the new center of the cascade. So the camera moves, you also want to move the cascades. And that's also what Simple Bake Update does for you. What Simple Bake Update does not for you is if you only want to partially update the cascade. This needs to be done manually. If you want to know more, check out the official documentation for details. Once you have the cascade update description, you allocate local memory for the scratch buffer, and then you call simple update, which does the actual update for you. If you call simple update, Pixelizer will use the built-in time slicing strategy, which means it will update the first cascade every even frame and the others every odd frame. If you need a different time slicing strategy, this is also possible, but then you have to access the lower level API. Again, check out the official documentation for details. Pixelizer also offers support for tracing, and this can be used for debugging. So you can verify that your integration was actually successful or not. There are different debugging modes, just different ways how to display the distance field. So you can display it as UVW, the number of iterations you're tracing to, the gradient, the brick ID. These screenshots are taken from a pre-release version of the sample that we will eventually release. Since it's based on a pre-release version, the actual output might be a bit different. That's not clear yet, but yeah, so it will be very similar. So you already can see here the visualization of the gradients, for example, or the brick ID, but that's what you can expect from the debugging functionality. For what can you use Pixelizer? Well, Pixelizer itself is just generating the sparse distance field that you then can use to find efficiently the hit point of array with the scene. What you do with the hit point is really up to you. Some examples are you can use it to compute global illumination, ambient occlusion, volumetric effects, or occlusion testing, but also anything else you might come up with is of course valid. To be honest, I'm actually really excited to see what you will come up with in the future. So we did some research work in how you can use Pixelizer to compute global illumination. And we always called it PrixGI. So it's still research, so it's not done yet, but we do have some screenshots. So on the left, you see the Resolve Diffuse GI. And then on the right, the combined, so the direct and indirect lighting combined into the final image. The basic idea is to use a probe-based approach. And you only have probes for voxels that touch surfaces. We know who these voxels are because voxels that touch surfaces point to a brick. And we just let them point to another probe, well actually to two other probes as well. So we added a direct light probe and a spherical harmonic probe. You can also see that the resolution of the probe is also user defined. So while a brick is 8 by 8 by 8, the direct light probe in our PrixGI is only 4 by 4 by 4. This approach does cover volumetric effects to some extent, because for them a probe from a bigger cascade would be picked. And from the bigger cascade means that this probe is further away from the surface. And then the basic idea is to populate the direct light brick from direct light information from the previous frame. And to update the spherical harmonic probe, we shoot a GI ray from the G buffer surface and let it traverse with the Pixelizer acceleration texture, which means first the ABB tree and then the distance field in the bricks. And then we update the brick information by sampling from the direct light brick where the GI would determine the hit point. This way we get rid of most light leading because the ray origin is on the surface. However, there are still some limitations that we are looking into. First is that the approach right now is basically a screen space plus, because the direct light probes are updated from screen space. We're also experimenting updating them with out of screen information, but it proved to be very scene dependent, so it was very difficult to get good trade-off for a general case. Also, convergence can be visible over time, and it tends to suffer from overshadowing for tiny geometry. But as I said, PrixGI is still under development. We are still doing research on it. But we thought anyway that it's worth to presenting the basic idea to you, so that you get a better idea of what you can use Pixelizer for, and maybe come up with your own solutions. And this is the end of the presentation. I presented to you Pixelizer, a library that generates in runtime a sparse distance field for any given triangle-based geometry. There are several options for you to tweak the distance field generation in terms of update performance and precision. Pixelizer is there to offer you an efficient way in finding the right hit point with the scene. The focus is really on performance, and it's especially suitable for effects that don't require the highest precision. So you kind of take a step back in precision, since Pixelizer provides an approximation of the scene, but you gain a lot in performance. And for some effects, this might just be what you are looking for. For example, chlorination typically does need the highest precision, the same for ambient occlusion. You can also use it to compute volumetric effects or to do occlusion testing. In this presentation, I present to you one way of how you could use Pixelizer to compute glow illumination on top. I hope that this serves to you to get inspired, and also that you come up with your own solutions. Pixelizer will be released in the near future. I hope you will check GP Open. We will announce it as usual, and yeah, Pixelizer will be part of FidelityFX, so it will be open source. We will provide a sample, and it will be also extensively documented so that the integration offered is as easy for you as possible. And now the only thing left to say is thank you for joining in and listening to my talking about Pixelizer. Thanks.